It's a good version of like a baby map, and it will build up to the bigger maps that we're going to do in just a second. So as we go through this, just copy it down. It's a good illustration of the concept of a map. What it does, it gives you parts, but they're all tied together now. So it's not individual random reactions that I'm just throwing at you, scattershot 10 of them, like your quiz was. They actually relate to each other. And you have to use the clues within the reactions to try to figure out what's where. So let's go ahead and let's just start filling this one in. If you can, start at the beginning, but sometimes you can't and you have to work backwards. On this one, I wouldn't particularly want to work backwards because I've got in this area here, see that right there? A ton of unknowns. I don't know what B is. I don't know what E is or D, and they're doing something to C, and I don't know what C is. So that's not where I want to start, right? I have no clue what's going on anywhere at all there. So let's start at the beginning, not right there. So I have an alkane, and I'm treating it with A, whatever A is, and putting a bromine on the tertiary carbon. What does A have to be?
HBr.
HBr is, it'll put a bromine on something, but for HBr,
BR2
I need
light.
an alkene. Yeah. HBr needs a C double bond C. So this is Br2 in light. That's all you can do to an alkane. Sort of stuck. So Br2 in light is A. I put the bromine on. Now here, go ahead. No, go ahead.
How do you know that the bromine is going to add to that specific spot and not another part of that whole alkene?
Okay, yeah, because I got a bunch of carbons, right? Bromine is very selective for the more substituted carbon. If you think back to unit 1, let me finish writing this down. So selective for the more substituted carbon. If you think back to unit 1, we had some selectivity numbers, and they were, if it was a primary carbon for bromine, they called that 1. It had a rate of 1 that it would react there. If it was secondary carbon, I think it's like 85 or 87. I honestly don't remember. It doesn't matter. About 87 or 85. I forget what. It's in your notes. If it was tertiary, a tertiary carbon, the rate was 1800. So if there's a tertiary carbon in your molecule, that's where that bromine's going to go.
Okay, maybe I'm missing something, but to me, it looks like there's 2 tertiaries.
They are. And why did it not matter where it went?
Symmetry.
Symmetry. It's symmetric molecule.
Okay, got it.
Normally, if let's say I'd put this on there, like another group right there, then I've got a mess because it will go to both and they'll give 2 different products, right? But this one, because I didn't want to deal with that, I did not draw that methyl on there. It's symmetric and it doesn't matter.
How do you recommend dealing with it?
Okay, let's see. You've got a dueling talking. Ali, why don't you go first?
I was gonna ask, how do we know it's not going to like brominate both like tertiary carbons?
You know, because what you typically do, it could, if you had enough bromine, what you usually do is you control that with a mole ratio. And so I would put in 1 mole of the alkane and 1 mole of the bromine. And the idea is that before a molecule that has already reacted finds bromine to react again, which it could, before that happens, I'll have the alkane find most of the bromine first. Statistically, the odds of something reacting twice are less than the odds of something reacting 1 time. But you would probably, if you were to like shoot it into a GC, let's say, and you could see a peak for all the different products, you would see a peak for the dibromo, but it should be small. And so that would be classified as an impurity.
Okay, thank you.
Okay, someone else had another question. Did it get answered in that?
No.
Okay, go ahead and ask it.
How would you address like the extra branch that you drew?
Oh, what you'd have to do, boy, it'd be bad because you would have two products, right? And you they'd have different boiling points because one's bigger than the other, right? Has more carbons. So you probably would end up, I suspect these would be a liquid. And so you'd probably end up having to do a distillation, and one of them would boil off before the other one. And so you would collect the two and you would take the one that you wanted. But you would somehow have to separate them before you could move on and take out just the one you want. So probably separate them based on boiling point by distillation.
Okay, thank you.
Yeah, you would. That's why I didn't draw the methyl. I didn't want to deal with it. So, okay, so we got this bromine. So we're doing good. Then we do some mysterious B to get a mysterious C. And we don't know what C is, but we're given a clue. So now here you have to look at your clues, which requires you to kind of know your reactions. Take a look at this product right here. The product from whatever D is a double bond O, right? It's ketone. But more notable than that, it's 4 carbons, right? And my bromo compound that I just made is 8 carbons. So what's happening to, what is the process that's occurring in D? What's happening there?
Ozonolysis?
Ozonolysis.
Yeah, it's like ozone or KMNO4 or something. It's a cleavage, right? There's a cleavage going on there. I'm getting one product. So I know that C has to be an alkene, right? Because I'm cleaving it. And it has to be symmetric. So it has to look like this. In order to get that cleavage product, C has to be this guy. Make sure I'm drawing it right. Yeah. Right? Has to be that. So that required me to work backwards to figure out what C was. Now, once I know that, I think, pretty comfortable with where to go. So a lot of you guys wanted to do ozonolysis, and that would be fine. KMNO4 would work fine too, but we'll do ozone, and then we'll just work it up with zinc. There it is. So what does B have to be? I went from the bromo to a double bond. What is B?
The base.
KOH.
It's base. Yep. It could be KOH or NaOH, some kind of OH and heat. All right. So that's good. Got that solved. Now we just have E that we have to answer. Oof. So C looks like this. I kind of lost C in the forest of stuff. There is C right there, right? And I do something to it, and I'm putting a bromo there on the molecule, on the side chain, and I keep my double bond. So I'm putting the bromine on, and it's allylic. What is E? I just did an allylic bromination. I see it popping up in chat. Good for you guys. It's NBS. N-bromosuccinimide in light. We'll do an allylic bromination, put a BR on, and keep your double bond. Okay, your first map under your belts. Any questions about it? All right, let's go to the others now. They're sort of graduate level maps.
There was a question in chat. I can read it if
Oh,
you'd like.
okay. No, I can see it right there. Would BR2 in light not work? No, it wouldn't, because a BR2 in light will put a bromine on an alkane. So in that respect, it would put a bromine on the alkane, right? But the problem with BR2 in light is the nature of the Br2, bromine immediately goes and reacts with double bonds. And so you could put it in, and that double bond is just going to chew it up, and you'll have 2 bromines sitting there and no more double bond. Okay, and so for that reason, we avoid that. You want to do NBS.
Would it function as if it was radical mechanism?
Br2 in light would, I don't know that you would ever get it to form a radical. The reaction with the pi bond is so fast that I think the pi bond would react with the Br2 before the Br2 could form a radical.
Okay.
Yeah, I don't think it'd be speedy enough to do anything like what you'd want. That double bond would just be gone with bromines in its place.
Is it the sorry? Is it because the pi bond is a good nucleophile? Is that
That's
why?
exactly it. Yep, the electrons are held pretty loosely, and they're very able to go out and attack electrophiles. So the minute Br got near it, it would react. Okay, let's do these others. A little bit bigger, a little more scary. Which one do we want to do first? I don't know. Let's do the first one first. This one's kind of interesting. You can't start at the beginning, right? Because you don't know anything about what is in this molecule. You have to start at the end and work backwards. That's okay. So we have aldehydes at the end, 2 different aldehydes. And we treated something with ozone to get those aldehydes. So in terms of H, we have to do H first. What functional group has to be in H? What must be in H? Not its actual like structure, but just what functional group?
An alkene.
It's an alkene, yeah, exactly. And it is just these 2 pieces here stuck together. So I'm not going to try to draw it pretty or anything. What I'm going to do, because if I draw it nice, it gets all messed up. I'm just going to draw the first one like this and go to a C, right? And I had an aldehyde there, but I'm going to make that a double bond now. And then the other one is 1, 2, 3, 4 carbons coming off of it. So there's the C, that aldehyde, and it's got 1, 2, 3, 4 carbons off of it. So there is my alkene. Not pretty, but there it is. And if I cut it in half, I would get those 2 pieces. So verify that's true, because if that's wrong, everything's wrong, right? It'd be super bad. Now I have some clue as to its stereochemistry. Let's see, do we know it's not an alkyne because no carboxylic acids? That's correct, yep. When you see the aldehyde and there's a cleavage, it can't be an alkyne. Okay, also a clue that it's not an alkyne, look 1 reaction back. So I look there, I treated something, G, with H2 and Linlar. So I know that H has to be an alkene. And I also know it's cis, right? So let's go ahead and let's draw that in. I fortuitously made it cis. It was accidentally, but I got lucky. Okay, it's a cis alkene. So I got that cis alkene from treating something with H2 and Linlar. So G has to be an alkyne, right? So this is actually not too hard to draw. I'm going to take where my double bond is and make it a triple. So we have that bottom part. We go up to a C. We'll go triple bond to a C. And then I'm going to do funky things with the angle because I don't want to lose my carbons. There it is. Okay, clearly it's linear, but I don't want to do that because it'll be all weird. Okay, if you want to make it linear, go ahead. I find it much easier so that I don't lose things to keep it just like that. Okay. So far, so good.
So it's okay if we leave our alkynes nonlinear?
It is. For the purposes of these maps, I really don't care. And a lot of times in books, they'll do something that drives me just around the bend. They'll write it like this, and I mean they're correct. So it just drives me crazy because I have a hard time figuring out what's what. You'll see this, then you'll see this, and then you'll see this. And I just, when that happens, I have a hard time. What tends to happen, people lose these two carbons right there when you write it like that. And if you write it like I am, it's your eye can really track where things are, which is more important than having the geometry written correctly.
Gotcha. Thank you.
Okay. Yep. Okay, then we go into, well, I don't know. We've got this thing F that made G, and we got that by treating E, which is also unknown, with NaNH2 and then adding F to it. I'm not sure what to do with that quite yet. So we're going to stop and just think. I look at that and I'm like, wow, I treated an unknown with an unknown to get G. That's a little bit too unknowns for me. I'm not quite sure what to do with that. So someone said the NaNH2 is associated with acetylide. I think so too. That's exactly what I think. What makes me think that is I'm going to say I get stuck and I'm like, well, an unknown and an unknown, I just can't. Come back to the beginning. I'm not quite sure what's happening, but I do know that I have a bulky base right there, right in the middle of all this. That tells me that this guy is probably an alkene. I'm probably making an alkene. I treat it with Br2, right? So this next thing, I'm guessing, is a dibromo. I have a dibromo compound. And now I'm good to go. I treated this dibromo with NaNH2 and then an H+. This is an alkyne. So your suspicion was exactly right. And we made an acetylide ion here. And then we added some amount of carbons to make our product. So let's say we had this, and let's just guess. What if this was the acetylide ion? And then the thing we added would then be, let me circle it in a different color, would be that right there, right? That would be added to it. And we're just guessing right now. I'm not sure if I'm right or not. We can always reverse it if we need to. So it would be like that, like a bromo. Okay, that would give me my product. But what if it was the opposite? What if I cut the other thing off? I said or, let's do or right here. What if it was the top half was the acetylide ion, so it went like this, and I had C, triple bond C, and that was a minus, and it reacted with that. That'd have to be the other possibility, right? Okay, take a look at those two possibilities, and what do you think is the best one?
Primary.
Yep. When you're doing a acetylide ion, you have to have it attack a primary alkyl halide. This option down here would give me E2. That's not what I see. So I am assuming that this is what's happening. I'm not sure. So we just keep running backwards. If it all works out, we guessed right. If it doesn't, we're going to have to go back to the drawing board and try again. Okay, so given this, I suspect that E is going to be this. It's my alkyne, and my alkyne is going to look like this. That's what I'm saying. Okay. Will you have reaction maps? Yeah, you will. There's one of them. Okay, it's not, this one's like a turbo map. It's not, it's the one you'll have is more like that. That's a little bit easier. You'll see in just a minute how it is. Okay, so we got this triple bond. I made it from a dibromo compound. Well, the dibromo must be this. I got that, and I have a C and a C, and I left myself 0 room for this. I'm gonna move it. Hang on, here we go. I'm gonna move this guy over here. And we have a bromine here and a bromine here. There's my dibromo. And that came from, going backwards, came from an alkene. So the alkene must look like this. Must be a C double bond C, just like that. Once you get over the hurdle of that E and F thing, it flows pretty smoothly. So I've got my alkene. All right. And I got it from a bulky base. So I have this, I have the 2 carbons. What is on them that the bulky base took off has to be a bromine. Now, in terms of where that bromine is, I'm not 100% sure. Let's, I could probably put it a number of places. So we're going to guess and we're going to test it off. Here's a question. Why did the triple bond turn into a single bond and then back to a double? Oh, where are we looking? Probably because I wrote it wrong. Let's see. Where is that you see that?
So C is a double bond, and then D is a single, and then E is a triple.
Right. So what we're doing in this whole series of C to D to E is we're making a triple bond. And the process for doing that is you get to a double where you want the triple to be. Then you put 2 bromines on. And then to get to the triple, I take those bromines off, and that's a double E2. So it's an E2 times 2. And that's pretty much the process you follow to make a triple, is you have to get to the dibromo. But to get to the dibromo, you have to have a double. Make sense?
Yes, thank you.
Okay. I'm going to put a bromine on somewhere and see how it goes. I don't know. What if we stick it here? What happens? I just put it there. I don't know where it goes. Let's just do that. If I treat that with a bulky base, yeah, I'd get my double bond. Now, for A, I treated something with HBr and peroxide, so I know A has to be an alkene, right? And so I'm going to go C, C. And HBr and peroxides, if I want the Br where I put it, right there, the double bond would have to be there. And then HBr and peroxides would give me that Br. Okay. There is a problem with this choice. Do you see what it is?
A and C are identical.
A and C are the same. Yeah, why would I have bothered doing that? So I just introduced a bizarro thing right there. I wouldn't do that, right? You wouldn't start with something, go through these gyrations and get it back, right? You may as well go out to lunch. So let's put the Br at the other carbon. This is the kind of thing a map does. You try something, you're like, oh, that didn't work. So let's, instead of the Br there, put it there. And then if I do that, I can take that double bond and I can put it there, can't I? It makes it different, it makes it an isomer. And then HBr and peroxides will put the bromine anti-Markovnikov. And then the bulky base makes a little more sense then too. So on maps, people get paralyzed because they're afraid that what they put down is going to be wrong. And as you saw, I did put down something that was wrong. And so what you have to do is you just put down something and keep running with it until it doesn't work anymore. And then usually it's a choice between one carbon or another, like ours. And when it doesn't work anymore, you're like, oh, it's the other carbon. So you put it on that one and run it backwards to see if it worked then. Okay, let's do one more map. So finish us up probably. This one's a little nicer. This is more like what the kind you're going to see, right? More normal. It gives a lot more clues to structure within it. Okay, that last one, you just had like one clue and then you had to fish around, try to figure things out. So this one, I'd start at the beginning and see how far we can run with it. And then if we get stuck, maybe go further on and start working backwards. Okay, so we have a bromo compound. We treat it with a bulky base. This will give us the Hoffman double bond. So write down what you think that should look like. It's definitely going to have a 6-membered ring and a methyl. Put that double bond where you think it should go. Okay, did you stick it up into the methyl like that?
Yeah.
Okay, good. Everyone okay with that? You're going to get the Hoffman less substituted product
Because of bulky base.
because of the bulky base, right? This thing right
Okay.
here, this is terp butoxide. All right, then we have something, it's a little different than what we're used to, KMNO4 and heat. What do you think that reaction is?
Cleavage.
Cleaving.
Yeah, it's a cleavage reaction, good. So we're going to break this guy off. If we have one carbon that goes away, that's going to be CO2, right? That's a gas. And just looking at the rest of what I have in here, that is not what we're working with. That's not what we keep. The other half is what we care about. So we have CO2 and I'm interested in the ketone half right there, right? So that's number 2. Then we're going to treat that with the product from 3. So we got to go hunt for 3. There it is. That feeds up into there. So I got to do a little work down on the side thing before I can do anything else. So I have a triple bond in as my starting material for this little side map. I'm treating it with NaNH2. Well, that's this is drawn weird, huh? Put the H out here. That's just weird. Make that your triple bond and put the H out there. That's just an acetylide ion. So it's going to be a C minus triple bond to a C, and then a C and a C like that. That's the acetylide ion. And while we're down here, let's finish up the rest of it. Let's do 4 and 5 too. So draw what you think should be number 5. So it's mercuric sulfate. It's an oxymercuration, demercuration, right? Can you isolate it? That's a good question. Typically you don't. So you know the Grignard reaction we did? We made the Grignard, we watched them make the Grignard, and then they had an addition funnel off to the side. And once the Grignard had sat for about 30 minutes, they put the acetone or whatever ketone they were using into the addition funnel and slowly added it. That's typically what you do. You would, in a round bottom, you'd make the acetylide ion, let it stir, make sure it's all done, and then you would just directly add the next thing to it. It's just too sensitive to try to isolate. It would be very difficult. Okay, what do you think 5 is? It's an oxymercuration. So I have 4 carbons here.
Ketone?
Good job. It's going to initially put an OH Markovnikov, right? So that's going to do an OH Markovnikov, but that's an enol, and so we're not going to isolate it, and it's going to go to a ketone. Good job. Okay, I don't think we ever used that in this map, but there it is. Now this next one, I never liked this one. It just seems goofy. NaNH2 is going to give you the acetylide ion, right? And then they treat it with bromocyclohexane. I almost think this has to be a typo. We took it out of a book, but that is that. I think they wanted you to have the cyclohexane attached to your acetylide ion, but there's a problem with that. What is it?
It's not primary.
It's not primary. Yeah, this is secondary. You're going to get an E2 reaction with this. So fine, we'll go with it. If it's an E2, you get a double bond on your ring, and you get right back your triple bond compound. Your alkyne comes back. I can't imagine that's what they wanted, but that's what it is. So there it is. Okay, so any questions on the little 3, 4, 5 thing? Okay, would it work if it was a CH2Br? Yes, it would. Maybe that's the typo. I don't know. The question was, if this was different, would it work? If it looked like this, like that, would then it work? And this is now primary, and it would work. And what you would have then is you would have, let's see, there's your CH2, right? And here's your triple bond attached and the 2 carbons. That would absolutely work. So I don't know, maybe that's what they meant. I don't know. That always seemed like a stupid part of a problem to me. You'd show them something that doesn't work, but there it is. Okay, we know what 3 is. It's the acetylide ion. It's going to react with the ketone. So let's go ahead and draw that out. I'm going to kind of expand it a little. And it will attack at the carbonyl. Electrons go up onto the oxygen and form an O minus. And then we do H3O plus and protonate it. So number 6 is going to be this. 6-membered ring, the OH from what was the ketone, and then a C, triple bond C, with 2 carbons attached. It looks just like that. Now let's say that you got to that part of the map and you know there's an acetylide ion and you know there's a ketone, and you look at it and you're like, I know it does something. I don't know what it does. And you're just like stuck. If you get stuck, look further down the map. Take a look. Let's say you're like 6. I don't know what 6 is. Take a look at this right there. That's a massive clue. You see your cyclohexane. You see an OH off of it and something with 4 carbons, which had to come from that acetylide ion. And that tells you what that addition looked like. Even if you don't quite understand it, you'll know that 4 carbon chunk added to that same carbon as the ketone. So somehow we arrive at number 6. Then to get to number 7, we're getting rid of the triple bond, and someone recommended hydrogenation times 2, and that is absolutely right. Hydrogen, palladium, platinum, nickel, not a poison catalyst because it goes all the way, so not Lindlar's. Then H2SO4 and heat, that's a dehydration. It's going to give us a double bond. So 8 will look like this. 4 carbons off there, 1, 2, 3, 4, there we go. Double bond in the center. And what is 9?
Ozone.
Cleavage. Oh,
It's a cleavage, and what did we use?
Ozone.
How do you
Ozone.
know that?
Because the hydrogen, it would
Right
be
there, right?
an OH if it was a KMNO4.
Yep, very good. Yeah, we see an aldehyde, right? And if it was KMNO4, it'd be a carboxylic acid. So we know this is ozone. And the second step is you can use zinc, or your book uses dimethyl sulfide, whatever. We know it's ozonolysis. So this map was actually a little kinder and gentler, and it is more like what the kind of thing you're going to see, with more clues in it than that one. That one's kind of fun, but a little bit rough.
I'm kind of confused. What was the purpose of 5 and 4?
I don't know. just to test your knowledge of reactions. Yeah, they're never actually used anywhere. So it was basically, I think, just to see, okay, do you know what this is going to do?